So it's FPGAs and low power. They've not always gone quite close together. Typically with FPGAs, you're not talking about this low power space. You're certainly not really talking the mobile space. Although we have FPGA design wins in some smartphones, but usually only for small RAMs. What I'm talking about today is a new paradigm in terms of programming FPGAs, which is the OpenCL flow, which typically has been used for CPUs, GPUs, but now we've taken that and produced an SDK for an FPGA as well. So before I start, I'm just going to have a bit of audience participation. So if you could put your hand up, please, if you've ever used an FPGA. Oh, so a fair amount. But not everyone. Everyone understand what an FPGA is? Some people. Anyone can spell it? So it's not a well-known technology. Not particularly well-known technology from software engineers. Okay? And that's what OpenCL does for FPGAs. It allows this technology to be used by a wider variety of engineers. So I'm going to talk a little bit about technology trends, what we see in the FPGA and programmable space, a little bit of an overview on FPGAs, talk on our implementation of the SDK, and then some of the benefits and case studies. So technology trends then. We've seen a significant amount of applications now moving towards an FPGA-based system, mainly because of the programmable aspects of it. Most applications now need some form of programmability, certainly in the development stage, and certainly now seeing that post-deployment as well. So we see that in areas where FPGAs have never played before, things like surveillance applications, automotive applications, things like this. And then we start talking about heterogeneous computing. There's been some very good presentations today talking about heterogeneous computing, talking about how computing has evolved. And what we can see is, CPUs, DSPs have gone from single cores to multi-cores, coarsely grained, massively parallel arrays like transputers, etc. And if you follow that curve, like that linear progression, you end up towards FPGAs. Now, FPGAs don't tend to be considered a computer element, but because an FPGA is a massive amount of programmable logic in there, that can be a bespoke processing element in a system. Okay. So an FPGA overview itself. FPGAs are built up of logic elements. What I've got here is a die sample of one, and they're big die. This has got 4 billion transistors on it. It's not the biggest FPGA we build. There are bigger ones than that as well. But they have thousands of memory blocks on there, thousands of DSP elements in there, so there's up to 4,000 DSP elements on an FPGA. Each of those is essentially a processing element, so more processor cores than a GPU, for instance. And also include high-speed transceivers, so you can get information into and out of an FPGA very, very quickly. We're talking 100 gig Ethernet, 400 gig Ethernet type systems relatively easily. If we take that trend on and look at where we are with SoC solutions, we've already heard this morning about various different SoC solutions where you've got multiple ARM processor cores in there. We are doing that now with FPGAs. So we have a variety of FPGAs, our Cyclone 5 and Area 5 SoC products, that are built on a 28 nanometer low power process, so a low power solution, that has within it an dual ARM Cortex A9 processor subsystem and a set of peripherals with massive amounts of connectivity to the FPGA fabric to build a very high performance computing system. And there you're going to use the benefits of the FPGA fabric for acceleration of application areas and the processor, where the processor works well for a lot of decision-making logic and things like this. Now we have a disconnect. We've got a FPGA programming model which is based on RTL, VHDL Verilog, or to the extent system Verilog or something like that, and processor programming model of C and C++. We need to find some way to bridge there. And that's where this kind of comes in for a solution for this is OpenCL, to have a unified design environment that allows us to target both. Now, will you get the ultimate in optimization by doing that? Probably not. You will always get better performance by hand-coded HDL in an FPGA. But you will get faster time to market, faster evaluation of architectural solutions. So our programming model, we've already heard much about this today in terms of OpenCL as a software programming model. It works very well for FPGAs because it is standard C, and it opens up a wide variety of programmers to be able to use an FPGA. And we're seeing FPGAs used mainly for areas where you're doing server-type hardware acceleration, typically. But there's nothing to stop that moving towards a more mobile, kind of handheld mobile medical type application areas in the future. So what we produce is a SDK for OpenCL Flow, taking the same OpenCL code, the host program and kernels, pulling that into our tool, and then delivering that into the FPGA as a binary programming file that can be loaded to the FPGA via something like configuration via PCI Express, a new configuration solution. We're calling the standard OpenCL calls, writing data from the host via an interface to the FPGA, running the kernels in the FPGA and reading them back into the host, and then building inside the FPGA all the logic you need to connect to global memory, produce your kernel accelerations and local memory on the FPGA. The host itself, essentially standard C code. All we're going to use is copy data from the host to the FPGA, run it, and then copy that back. Now that doesn't necessarily have to be by PCI Express. It can be by any interface we would like moving forward, but currently our implementation is using PCI Express as the interface. And that can be up to PCI Express Gen 3 by 8 lane interfaces for that. The kernels themselves, we've got, for instance, here a simple example with a couple of floating point numbers being added together, vector addition. What we deploy is a deep pipeline methodology of that in the FPGA, so multiple parallel threads running on the FPGA itself, and then using the keyword extensions from the OpenCL to define the parallelism and the capabilities we want in the FPGA from the OpenCL code in the first place. And what also is very useful from an FPGA point of view is you can debug that code using both the FPGA, a CPU, or a GPU by targeting different architectures. And we've seen that that is something that is a useful methodology for system development to get the right architecture. Now, FPGAs, because of its programmable nature and because the size of the FPGAs can sometimes take a certain amount of time to compile. The place and route of an FPGA is an NP-complete problem and can take some time. So we want to make ways of developing this solution so it's a fast compile. And the way we've done that is by taking the hardened interface logic, so the PCI Express, which is a hard IP in an FPGA, external memory controller and PHY interfaces, and locking those down as a place and route. So they'll be locked down as an individual place and route. The OpenCL compiler will take the code, your OpenCL code, and implement it as a block within the FPGA with one of our tools to produce the global interconnect, the connections between the global memory and the kernels themselves, and also the local memory interconnect that would be shared by the various work groups. The tool itself will produce a HDL file that will take your OpenCL code with your arithmetic, your various expressions in it, and wrap around it load and store functionality to make it a lot easier for those kernel blocks to be able to move the data and produce the deeply pipeline architecture. And as you can see here, this is a simple vector arithmetic where we've got a deeply pipelined architecture with various threads moving through the device so that we've got a very efficient architecture for implementing whatever application is you're trying to implement in the FPGA. The benefit of this is that a designer, rather than going from your C and going straight to gates or going straight to the atom level of the FPGA, is that you can then have a look at this kernel HDL and it will be readable to a point where you can see the functionality and how it's being deployed into the FPGA. And it also means that the follow-on processes that go through our Cortex 2 design software, synthesis, place and route, assembly, and timing analysis, are all a standard flow. So it's not taking much different to what someone would be doing within an FPGA flow anyway. So the benefits of using OpenCL in the FPGA, well, the key one there is productivity. So by using a high-level language, you do end up with a much shorter development time, much faster time to market. You also, with a high-level language, allows you this kind of portability across devices. So you can, in your architectural definition stage of a particular system, decide, I can either use an FPGA for this or I can use a GPU for this, and actually go through and look to see which is the most optimal solution. We see significant benefits in terms of performance and low power for an FPGA in these solutions compared with things like a CPU or like a desktop class GPU. We're talking typically here somewhere in the region of 1/5 the power of comparable solutions in those spaces. And last but not least, this is a very programmer-friendly solution for designing FPGAs. So as we saw earlier, there's a few people in here who've used an FPGA before, and there's a few people who haven't. This technology and the power it can give to you in terms of your design is now opened up to you by a new interface. So I wanted to show some case studies and some examples of this, and I've got some white papers here that go through in more detail of these, so I'll be fairly high level on this. But one of the areas where we've seen an application that is by far and away a useful solution for an FPGA is cryptography and things like encryption. So we've got an AES encryptor block here, developed by one of our board partners, Nalitech. They've shown the throughput of this core using Xeon processor or AMD GPU and their particular FPGA accelerator based on Stratix 5. And you can see here at 42% utilization, so there's the ability to load the device with more cores to do a similar thing, 5.2 gigabytes per second of throughput in comparison to 0.33 from the GPU and the CPU itself. And this is a very useful example for where the FPGA fabric fits in nicely. The advantage for the FPGA is integer arithmetic, this coarse-grained operations, and then the complex decision-making of the AES solution can be very, very closely tied to the data and optimized. Another example here, this is maybe more suited to the guys down the road in the city. But we're looking here at option pricing application where we're using a Monte Carlo simulation, well suited to the FPGA, diverse data, and can be moved into separate kernels and stamped into the FPGA. And what I want to highlight here is not just the performance advantage. So we've got here, this is the millions of simulation per second, 170 million simulations per second, but also the power consumption benefits. So this solution here, okay, it's not mobile levels of power consumption, as we've heard this morning, but 23 watts compared with a couple of hundred watts for a competing solution. So it's all about efficient computing in this case, where we're talking about 7.4 million simulations per watt versus almost a quarter of a simulation per watt. Similar things here with document filtering. So a Bloom filter that will be implemented by something like a newsletter scanning application or even kind of a robot for Google, etc. Here you've got the benefits of integer arithmetic and flexible memory configuration that allowed us to build a very efficient structure inside the FPGA for sorting this documentation. Similarly, I have a white paper that explains this in more detail, but the sort of comparisons here, you can see similar sorts of levels of power, 25 watts versus 215, 130 watts, and the millions of transforms per second is significantly higher than the CPU, but the power efficiency per operation is much better as well. And this fits quite nicely when you're looking at server applications where you have limited power, where you have to stick within a PCI Express power budget of 25 watts, for example. You don't have the ability to go to the extra power consumption. Now, we've got another example here. This was developed by a spin-out company from the University of Warwick. This is a company called Go HDR. And we took their code and ported it to OpenCL. It was implemented in both a GPU and an FPGA, and you'd think this would be an instant win, hands down, for a GPU. It's a video application doing HDR. What we've seen here was we took their code, they went to our Toronto Technology Center, they took the code and started porting it to OpenCL. The first day, nothing worked. Okay, we've got a little bit of a problem here. The second day, they thought they may have a bug, so they took that code, the same code, put it back into the GPU, and found they had a bug. They fixed the bug in the GPU, and then ported that back in another day to the FPGA. Okay, that sort of operation would take somewhere to hand code 3 to 6 months of work, and it was done within a week. Okay, the efficiency wasn't the same as the GPU in that particular application. It took about another 2 weeks of work to change the optimization of the code to fit and get the same sort of levels of efficiency of the GPU, but at lower power consumption. And similarly, my final case study is a Fir Filter. Now, this is a slightly weighted towards FPGA solution. FPGAs are very well suited to digital signal processing type filtering applications, FFTs, etc. But this can be done in both FPGAs, GPUs, and CPUs. So it's a very good example. What we've actually done here is did an absolute performance comparison here. So this is the number of samples per second running at 170 megasamples per second in the FPGA compared with the CPU and GPU. You can see the CPUs and GPUs, as the number of taps increases, they get more efficient, but nowhere near to the same sort of performance levels of the FPGA. And the FPGA falls down in terms of performance only when the number of stamps of the kernel becomes too large for the FPGA, and you have to produce a different architecture by TDMing the data through the filter. And you can see that change there. And then in terms of power consumption, we're leaps and bounds better than the GPU and CPU power consumption, and as the power ratio here. Now, you could say this is a tailored application for FPGAs. Well, we could do that. We're marketing. We can actually try to implement that sort of benchmark. But what we did do, we did the signal processing that allows you to take this from an O to the N operations for a processor and turn that into an O to a log N operation, which is probably the most efficient way of doing that within a processor. And there are many, many different applications that are of a similar vein to this type of Fir Filter application, where it's well suited to be able to accelerate it by an FPGA. So it is a simple application. It is an application that is well suited to the FPGA, but it does represent that larger class of applications. The important thing, I think, is that the fine-grained parallelism of the FPGA, the ability to produce a bespoke architecture for your accelerator, and the areas of the FPGA you're not using are drawing no power, gives you a very efficient implementation. And what you can see here is that there are going to be other systems that will have this same sort of processor type applications that can be accelerated with an FPGA solution in a similar manner. So it's a relatively true to life application area for this area. We're seeing significant draw from areas of high performance compute. where the FPGA is becoming part of the compute flow. In a lot of some supercomputers, the FPGA has been a portion of the communications infrastructure, which is something that FPGAs are very useful for some time now, and it's starting to become much more a part of the actual raw core computer architecture. There are some other extensions to the OpenCL spec that we are proposing, things like streaming, like channelized architecture, that would suit the FPGA even more to be able to produce a much lower latency type of solution, not having to go backwards and forwards across a PCI Express bus, being able to do that sort of computing directly into the processing element from, say, 10 gig Ethernet or sort of input, which saves a lot of the time going backwards and forwards across the parallel buses of the serial buses of the PCI Express. So the only thing I want to add is if people are interested, OpenCL is brand new. We launched this at the beginning of this month. The SDK became public. There are boards available that support it. Some here. If anyone would like to come and talk to me in further details on that, please speak to me at the end in the break.